Welcome to Pavinars, webinars for the pavement community. My name is Andrew Bram, and today we're going to talk about SAMI, or Stress Absorbing Membrane Interfaces and Other Stress Relief Asphalt Layers. And this is the 2021 update. The original SAMI Pavinar was held and recorded on October 1st, 2013, and it was posted on YouTube on September 6th, 2018. It currently has over 1,000 views, so an update is warranted. Now, what we're going to talk about today is a background of SAMI and other stress relief interlayers, and this will include mechanisms of reflective cracking and some basic introductions to reflective crack control treatments. We're then going to dive a little deeper into different types of stress relief layers, including geosynthetics, SAMIs, and reflective cracking relief interlayers. We'll then spend some time quantifying the benefits of these stress relief asphalt layers, and we're going to hone in on a Louisiana report that dug deep into predicted service life and an economic analysis of various stress relief layers. Then finally, we're going to end with some field and full-scale experiences. We're going to look at two case studies in the United States, one from Nevada and one from Texas. We're going to look at two case studies from Europe, one from the United Kingdom and one from Switzerland. And then we're going to look at some work that's been done in Brazil. So let's start by asking the question, why are stress relief layers important? Well, when an asphalt concrete overlay is placed on an existing Portland cement concrete overlay or an asphalt concrete roadway, there is a possibility for reflective cracking. And that's because the existing pavement often has either cracks or joints in that existing pavement. And so you can see here this picture from Ishandawe, taken at the University of Illinois. You can see a Portland cement concrete pavement with a joint in the middle, and an asphalt concrete overlay was placed on top of that Portland cement concrete pavement, and there's a possibility that that joint will cause a reflective crack to form. And these cracks reflect into the new overlays. So that existing joint, when wheel loads go over it and when there are thermal changes, will start moving up into the asphalt overlay, and eventually you'll have a crack that is on top of where that existing joint is. Now in this picture, you can also see in the red box, there's actually a different type of asphalt concrete mixture. And that's because this is a stress relief layer that was placed between the overlay and the original pavement. Then on top of that overlay was the asphalt concrete overlay. And this stress relief interlayer provides a buffer for reflective cracks. So when we focus on the pavement specifically, we can zone in and think about how do wheel loads and how does thermal contraction influence these cracks. Well, as a wheel goes over a pavement, there are bending and shear stresses that occur in that pavement. And there is also a thermal contraction that causes a tensile type failure in that pavement. So you can see by these arrows, the thermal contractions cause the pavement to want to open because the pavement shrinks, and the wheel loads cause the pavement to go up and down, and this causes bending and shear stresses. Now there's also some vertical movement due to thermal contraction and some horizontal movement due to wheel loads, but in general this is the simplified story of what's going on under loads. It's important to understand, how do these cracks that are reflecting through the asphalt concrete layer, how do they move? Well, it starts with crack initiation, and crack initiation is the formation of microcracks. And when we think about microcracks, you want to think about a region. There are many microcracks over a region, and over time, these condense into a single macro crack. And once you have that macro crack, you start propagating the crack. And the macro crack starts at the base of the overlay in reflective cracking, and over time it moves upward through the overlay. Now there are various experiments and analysis techniques that dig into this concept of crack initiation, crack propagation, crack movement, these type of things. And this includes Paris's law, pseudo work, fracture energy, tensile strength energy, and strain energy release rate, and flexibility index, cohesive softening, and power release rate. Now, the details behind these various experiments and analysis techniques are beyond the scope of this Pavinar, but if you're interested in these concepts, I encourage you to take a look at a white paper called Fatigue or Not Fatigue. That is the question, a white paper. And if you search for this on ResearchGate, it is available for download free of charge. Now, what sort of ways have we developed to try and either ideally eliminate or at least slow down the movement of these reflective cracks? Well, we have geosynthetics, and geosynthetics are thin, flexible sheets of synthetic polymer. They can be polypropylene, fiberglass, or nylon. You have either woven or non-woven varieties, and they include a fiberglass mesh, a non-woven matrix, which are about a ½ inch by ½ inch wide. So you can either have a woven mat or a mesh type configuration with geosynthetics. Stress absorbing membrane interfaces, or SAMIs, are usually either asphalt emulsion or hot applied asphalt binder placed on the road, and you can potentially modify the asphalt binder with either SBS, styrene butadiene, styrene, ground tire rubber, or other modification techniques. You may use fiber between the layers of asphalt emulsion or the hot applied asphalt binder, and you place coarse aggregate chips on top. A reflective cracking relief interlayer can be either fine graded asphalt concrete, which can be modified with polymer if you desire. And there are also different names for reflective cracking relief interlayers. So some articles I read use the term SAMI, which I believe is not quite technically correct, but you'll also see crack attenuating mixtures, stress relief asphalt mixtures. There's a proprietary product that was developed quite a few years ago called Strata, and these are all types of reflective crack relief interlayers. But remember, all of these materials, geosynthetics, SAMIs, and reflective crack relief interlayers, are all designed to be placed on top of an existing pavement and underneath an overlay in order to either eliminate or slow down the reflective cracking. And the next section will dive deeper into these treatments. This is just a very brief overview. So let's move on to those digging deeper into each type of stress relief layers. And let's start with geosynthetics. Geosynthetics can be geotextiles, which is a paving fabric. It can be geogrids, which you can see on the right. You can also have fiberglass material or geocells. You have geomembranes, geonets, and geocomposites. So there's a whole bunch of different types of geosynthetics out there. And when we think specifically of pavements, geotextiles, geogrids, fiberglass, and geocomposites have been used for reflective cracking. So as you're reviewing literature, you'll probably see these types of geosynthetics mentioned. So for example, for paving fabrics, this is needle punched and non-woven. It's 4.1 ounces per square yard or 4.6 ounces per square yard, depending on the thickness of the fabric you're laying. And you want it to meet AASHTO M288. You can see here it's being placed on an asphalt binder, and it's often saturated with asphalt binder. And this not only allows it to be a stress absorbing interlayer, but with this absorption, it can also act as a moisture barrier. Now, one of the common questions about this material is, can you mill it later, and can it be recycled into future mixes as reclaimed asphalt pavement? And there are paving fabrics that are specifically designed to be millable and recyclable, but that is something you definitely want to investigate before placing any particular brand. Now, moving to geogrids and geocomposites, these are no longer a fabric. This is more of a grid type material. These are non-waterproofing, and that is because they just use a pressure-sensitive adhesive and a very light asphalt concrete or asphalt cement tack coat. You can have multiple strengths of geogrids and geocomposites, and the grid embeds into the overlay. So you can see in this picture, you're placing hot mix asphalt on top of the geogrid, and that hot mix asphalt will go down into those cells and embed itself into the geogrid. So those are all non-waterproofing options. For waterproofing options, you can have a composite of a grid and a paving fabric, and it's generally laminated prior to delivery. And you want to make sure to place the fabric side down on the asphalt cement tack coat, and then the grid again embeds itself into an overlay. So you can imagine this open geogrid and geocomposite really isn't waterproof because it has these large cells in it. So if you do want the waterproofing benefits, you want to make sure to use a paving fabric in addition to the geogrid. Now, SAMI's, stress absorbing membrane interfaces, you generally place some sort of seal coat binder down, and this is generally polymer modified. And as I mentioned, this can be hot applied asphalt binder or it can be asphalt emulsion. And you can use ground tire rubber, you can use SBS polymer, and you can also place fibers in between binder layers. So you can put a thinner layer of either hot applied asphalt binder down or asphalt emulsion, then place some fiber, and then place another layer of asphalt binder or asphalt emulsion. So there's various ways to modify the seal coat binder. You then place your coarse aggregate chips, and essentially this turns into a chip seal. You put a pneumatic tire roller over it, you orient the particles, you sweep it, you let it sit for probably about a week to make sure all the water has left the system, and then you place your overlay. And these SAMIs retard crack propagation, and it also improves the tensile strength at the bottom of the overlay. So earlier I mentioned that you can have some horizontal stresses at the bottom of a pavement layer due to wheel loads, and that is because of a bending stress. And those bending stresses make tensile stresses at the bottom of your layer. And these SAMIs can help improve that tensile strength because it's a very rich layer. And then finally, the third type is a reflective cracking relief interlayer. And this is a dense, fine aggregate mixture layer, and it may or may not be polymer modified. It's placed on top of a deteriorated pavement, and then you place your hot mix asphalt overlay. And it protects the pavement structure from both moisture damage and it delays reflective cracking. Now, when we say fine aggregate mixture, we usually mean greater than 98% is passing the 3/8 sieve, which is the 9.5 millimeter sieve. So almost a sand mixture, but a very fine mixture. Now that we've had a pretty in-depth introduction to the stress relief layers, we're now going to go over some of the benefits. And we're going to start with a very nice study from Louisiana. So they first looked at paving fabrics, and when they were predicting the service life of various paving fabrics, they looked at 3 sections because only 3 sections provided enough data for performance analysis in this Louisiana study. And they found that all 3 projects showed a positive performance versus the untreated sections in this study, and the improvements ranged from delaying the reflective cracking anywhere from 4 to 5 years. They also looked at fiberglass grids, and they placed it in 2 different configurations. One was a complete road system, and this is where you place the fiberglass grid across the entire existing pavement surface area, so you cover all of the existing pavement. But you can also place this only in specific locations, and this is called a strip application. And this is where you just place the grid over where cracks are existing in the existing pavement. Now, the Louisiana study only looked at the complete road system, and they looked at 13 different sections. And they found that 8 of those 13 sections showed the untreated section outperformed the treated section anywhere from 0 to 7 years. And they also found that 5 sections showed that the grid outperformed the untreated section by 1 to 6 years. So you can see this is a pretty big mixed bag. Some of the untreated sections outperformed the grid section by 7 years, but some of the grid sections outperformed the untreated sections by up to 6 years, and some showed no difference. So this is really a mixed study, and if you're interested in fiberglass grids, I really encourage you to take a look at this report because there's a lot of interesting details and discussions about this in particular. And they also looked at 3 sections for SAMI in the state of Louisiana. And one section showed a positive improvement of about 5 to 10, excuse me, one section showed a positive improvement of about 10 years, and 2 sections actually showed a negative improvement of 3 to 5 years compared to the controlled section. So again, kind of a mixed bag. And then finally, they looked at 3 sections of reflective cracking relief interlayers, and they showed that one section showed a positive improvement of about 7 years, and 2 sections showed no improvement. And in the report, they actually classified this as a negative contribution because, of course, it costs a little more money. And if there's no improvement, then it's not a positive contribution. Now, after they had gone through all those performance analysis, they did a very comprehensive economic analysis. So they found that for paving fabrics, they increased the costs from anywhere to 2 to 13% of the projects, and they account for approximately 8% of the hot mix asphalt overlay cost on average. The fiberglass grids increased the cost anywhere from 2 to 128%, and on average, it accounted for 48% of the overlay cost. The SAMIs increased the cost anywhere from 8 to 23%, and it accounted for approximately 14% of the HMA overlay cost on average. And then the reflective cracking interlayer increased the cost anywhere from 25 to 58%, which is about 39% of the HMA overlay cost on average. So this is a very nice study because they looked at both the performance perspective and they looked at the cost perspective, which is very difficult to find in one study. So if you read Run Report from this Pavinar, I encourage you to search FHWA backslash LA period 11 backslash 478. And this report is available free of charge to download from Louisiana. And again, a very, very nice study. Highly recommended. Now, finally, we're going to move from the benefits to some field and full-scale experiments that I was able to find. Now, let's start with Nevada. And in the state of Nevada, they looked at 3 field sections, and they placed an overlay over an experimental stress relief course, or ESRC. Then they placed a 2-inch overlay and a 3/4-inch open graded friction course, or OGFC. They also placed the traditional Nevada reflective crack relief interlayer, which is Nevada DOT SRC-T3, plus the overlay and OGFC. And then they did a control section, which was simply a 3-inch overlay and a 3/4-inch OGFC. So these are the 3 field sections they placed with an overlay, and then they took cores from these field sections. So you can see here a picture of the OGFC, which was on all the sections, a picture of the SRCT3, which is the Nevada DOT reflective cracking relief interlayer. They looked at the control section, the T2C, and then they looked at the ESRC. So some very nice images there of the cores that were taken. And the cores were tested for thickness and air voids, and it was tested on the Texas overlay tester. And then from a field perspective, they found that there were no distresses absorbed on any of the sections over 13 months. And if you want more information on this, I encourage you to take a look at this journal article, Habush et al., titled Reflective Cracking Relief Interlayer for Asphalt Pavement Rehabilitation from Development to Demonstration, and this was in Road Materials and Pavement Design, RMPD, in 2017. So the first half of this study looked at the cores and looked at examining the field section, and the other section went to the lab. And they used plant-produced lab compacted mix. They tested for beam stability according to Nevada T303. They looked at dynamic modulus in the AMPT, and when they wrote this paper, it was AASHTO TP79, but now it's AASHTO T378. They tested flexural beam fatigue, AASHTO T321. They tested the overlay test in the AMPT following Texas 248F, and they also quantified rutting via a repeated load triaxial test. And you can see here a picture of the overlay test in the AMPT, where you have a fixed steel plates with your aluminum plates and then the movable steel plates. And the sample is glued to the face of that, and you pull on that in the AMPT. And in short, they found that the ESRC performed equal or better to the SRC T3 in all of these lab tests. But again, on the previous slide, I showed the entire citation. I encourage you to take a look at the paper for all of the details. Now in Texas, they have developed the Crack Attenuating Mixture, or CAM, and this is intended to reduce reflective cracking. And here's a nice picture provided by Tom Scullion. And on the left-hand lane, you can see this CAM mixture. The general properties are you have a binder content at a minimum of 7%, and it's usually placed at 8%. The design VMA is a minimum of 17%. There's various Hamburg wheel test minimum based on the PG binder grade. So if it's a PG 64 high temperature grade, it's a minimum of 10,000 cycles. A PG 70 is a minimum of 15,000 cycles, and a PG 76 is a minimum of 20,000 cycles. The overlay test must pass a minimum of 750 cycles, and this has been highly successful on both placing on top of rigid and flexible pavements. It's been placed on interstates, state highways, and farm-to-market roads. And then also it has motivated other states to develop similar mixtures. Like you saw in the previous study in Nevada, they have a special interlayer mixture. So really Texas kind of led the way in developing this mixture, and they have various reports available online. If you just search Texas Crack Attenuating Mixture, there's many available. Texas has all their state reports online, which is a very nice resource. And you can also take a look at TxDOT Special Specification 3000, which goes over all the details for the Crack Attenuating Mixture specification. Now moving over to the United Kingdom, they used a medium scale wheel tracking machine, and you can see an image on the right where there's a wheel running over a sample and you're measuring deflections with an LVDT. And this beam is placed on a rubber mat, and they tested at 3 temperatures. They tested at 10 degrees Celsius, 20 degrees Celsius, and 30 degrees Celsius. The materials they used, well, they used anywhere from a 40 to 80 millimeter overlay. The 80 millimeter overlay was the control, so there was no interlayer. So they used 3 different configurations of interlayers. No interlayer, which was the 80 millimeters. Then they used 20 to 30 millimeters of SAMI, and they used 2 proprietary mixtures, and they compared that to 20 to 30 millimeters of sand, asphalt. And when they had those 20 to 30 millimeter thicknesses of the interlayer, they then had a thinner overlay. And then they had a 10 millimeter base layer. And this is what had the existing flaw in it in order to try and quantify the reflective cracking. And they found that the 2 SAMI mixtures retarded reflective cracking at the higher temperatures. In fact, they found that it was optimized at 20 degrees Celsius. It did retard at 30 degrees Celsius, but they didn't see any benefits at 10 degrees Celsius. And they also found that it was actually more effective in thinner lifts, which is interesting. So when they had a thicker lift, that actually did not retard the reflective cracking as well. And they also found that these mixtures increased deflection. So it's kind of a trade-off. You are retarding reflective cracking, but there is a little bit of increase in deflection. And you can find all of the details in this paper, Ongundape, Investigation of Crack Resistance Potential of Stress Absorbing Membrane Interlayers, or SAMIs, under traffic loading. And this is published in Construction Building Materials in 2013. Now, moving over to Switzerland, they used different SAMI mixtures on an accelerated pavement test. They used an MLS 10, which applied 5,000 loads per hour at 65 kilonewtons. And what they did, this is a very interesting study. I enjoyed reading this paper tremendously. They placed a wearing and a binder course over unbound gravel, and they applied 3,000 cycles of the MLS 10 to that pavement. Then they placed glass fiber grid, SAMI, and a wearing course to that existing deteriorated pavement and applied 4,000 cycles. So they deteriorated a pavement in the lab, and then they placed this glass fiber grid and SAMI combination and saw what it did after that was placed. So it's a very nice study, and you can see on the left, there's a reference section and the grid plus the SAMI section. And moving from the left to the right, there's 5,000 cycles, 150,000, 200,000, and 300,000 cycles. And you can see as the cycles increase, there are some transverse cracks and longitudinal cracks that start developing. And they found that overall, that glass fiber grid and SAMI combination reduced the rutting overall, and it delayed the cracking. So there were some benefits seen from there. And this can be found, all the details can be found in Arigata et al. Influences SAMI on the Performance of Reinforcement Grids, which is published by Rylam in 2016. And finally, moving to Brazil, they did a very nice field experiment where they looked at SRAM, and this stands for a stress relief asphalt mixture, or SRAM, and this is a fine graded high polymer mixture. And they placed 3 sections in the field. They placed 2.5 centimeters of SRAM plus 5 centimeters of HMA, and they compared that to 7.5 centimeters of HMA, so the same thickness, but then also slightly increased thickness of 10.5 centimeters. Now in the lab, they ran a whole bunch of rheological property tests, which is very interesting, and they ran the SCB, the semicircular bend mix test at 15 degrees Celsius in a monotonic fashion. So they did a whole bunch of lab tests, but they also looked at this field, and they found that after 29 months, the SRAM showed lower reflective cracking. And they actually have a very nice graph here that demonstrated that. So you can see the thinnest HMA layer, the 7.5 centimeter, by far shows the highest percentage of cracked area. It got up to 48.1 after 29 months. Whereas the 10.5 centimeter only had 18.7, and the SRAM plus the HMA only had 12.2. So you can quite easily see the impact of the SRAM and how it does reflective crack a little bit, but it's less, and it's certainly delayed over having just a normal overlay or even a thicker overlay. And you can find much more about this in Gaspar et al. The paper is titled Highly Modified Asphalt Binder for Asphalt Crack Relief Mix, and this is in Transportation Research Record in 2017. So lots of additional reading if you are so interested. So in summary, for SAMI and other stress relief interlayers, we went over a background of reflective cracking, we went over the basic types of stress relief asphalt layers, some of the benefits, and then we also looked at multiple field studies and lab studies that tried to quantify some of these benefits. So thank you very much for joining me today. I hope you have a wonderful day.